Is big red button good? It's good. Great. Okay. I don't know if you could see the big red button. All right. So let's talk about what we've got going on. So we have an exam on Friday. Okay. And then there's going to be a review session on Wednesday. Okay. What's the exam going to be on? Exam on Friday. Everything after 12.4 that we've covered. Okay, 12.4 in the book. And the 12.4 was how to calculate a bunch of different types of concentrations, right? That's where we ended up on the last exam. So molar, parts per million, parts per billion, mass percent, all the various stuff we did on the last exam.
So everything that wasn't on the last exam.
Yes, in other words, everything that wasn't on the last exam that we've covered since, not before stuff that I might not have covered, right? Right. So the class is cumulative and builds because we use what we learned previously to build into the next thing. But I'm not going to go back, and if I'm going to go back and ask you something from a previous exam, I will let you know. Okay. That would be something I felt we missed and people did really badly on, and I have time to cover. It's that sort of thing. So I'm not going to. My goal is that you are not surprised by what's on the exam. Right. I'm going to work to get you a practice test. Okay. It's the first time. I don't know if you guys got the feeling for this. I probably shouldn't have been. It's the first time I've taught this class in 2 decades. All right. I have taught it. I know the material, but I've taught it a bunch, but not in a long time. And so I don't have practice tests. I can't give you a test from last year. Okay, so I'm going to have to make up the practice test and make up the answer key for it because I'm going to take the even problems out of the back of the book for which I don't have answers, and that's going to take time. And so you probably won't get it until Wednesday. Don't wait for it, right? You got to be practicing before then. We're also going to have a homework due on Wednesday. Okay, at 7 a.m. Yes.
What is the review session?
The review session is in class.
Oh.
It's class. I'm going to come in, I'm going to say what questions you guys have. Okay, and hopefully you guys have a bunch of questions. I like to have those things be student driven. So otherwise I'm just going to pick questions. But I will probably not have written the exam by then. So I would pick questions that are most important. But what's most important? You saw it on a quiz. That's important, right? So you should definitely know how to do everything you've had on a quiz so far. All right. Then there are things beyond the quiz, maybe if I have time. Right. I have to give you. I want to give you an exam that you could finish in the available time that people aren't feeling time pressure.
So the help session is on Wednesday and not Thursday.
There'll be a help session on Thursday too. So I have the luxury this week that my biochemistry laboratory is actually due on your own. It's kind of spread out. It's where they have to kind of come in. You have to coordinate 3 days worth of stuff. When you get to biochem, you'll experience that. But what it means is that I'm not teaching biochem lab officially this Wednesday, and so I'm going to have office hours. I'm going to go ahead with Monday and Wednesday, 1:15 to 3:15 p.m. if you'd like help. Okay, so I've got that. I probably won't bother with the office hours on Friday because nobody's going to come on Friday before spring break, right? Much less a Friday. But so that I've got those office hours this week, and I will have the Thursday help session. This is your last ditch chance to get help before the exam, right? Try to work ahead in terms of studying so you can ask questions multiple times. But Thursday help session, 7:30 p.m. on Google Meet. So lots of opportunities to get help. And if you want to get help, I can probably be available on Tuesday as well, right? I'm going to probably have to come in at some point to help get the stuff set up for biochem lab. And so that's going to have to be by appointment though. All right, so let me know if you can't make those, you want to meet on Tuesday, let me know and we'll figure out a time. Questions about stuff we're doing? Okay. So big scary exams coming up, lots of important stuff on it. What we're going to cover today is we're going to cover ICE tables. Okay, the ICE stands for initial, change, and equilibrium. Okay, ICE tables are a way to calculate what the concentrations are of reactants and products at equilibrium. All right, and students often find these challenging. So I mean, you're going to have some homework, but I encourage you to practice these. There are going to be three things that we're going to be doing today that are important for ICE tables or important for calculating changes at concentration. And so you need to make sure that you have these things mastered. You want to try to master these things. So set up the ICE table. This is like a setup before you solve the problem. Okay? There is a using the quadratic formula. All right, I hate the quadratic formula. It's brings like bad flashbacks from undergrad. But using the quadratic formula, and then you can avoid using the quadratic formula in certain situations. So there's an approximation to avoid using, can't always do it, using the quadratic formula. All right, and you are going to have to calculate the using the quadratic formula by hand if I put it on the test. And like I said, told my past class, I need to talk to Dr. Anderson and see how she feels about just giving you an approximation problem instead. All right, but you will get an ICE table problem, okay, on the test, either using the quadratic formula or using the approximation, or you might get something doing both. All right, questions on this so far? We haven't really talked much about what it is. So let's look at what an ICE table is. I'll give an example. So let's say I had a reaction that went like this. I have A plus B goes to, let's use the one we put up there, 2C, right? 2C plus D. Okay, I can make an ICE table for that. I want to figure out what the concentrations are at equilibrium. So I've got initial concentrations of everything. I have how they change going to equilibrium. And then I have what's the equilibrium value for these. Now, if you're in lab, what you're generally doing with a reaction is you dump A and B in and then you see how much you have at the end, right? That's how we would do it. A and B, and you don't have any C and D. So let's pretend that we had 0.5. I get this out of the problem. All right, the problem would say there's 0.5 molar, and we're going to practice a bunch of problems, so you get other examples here. But let's say we have 0.5 molar. Let me give it two significant figures. Molar A, I've got 0.20 molar B, and then I have 0C and 0D at the beginning of the reaction. All right, so I've got all reactants. Which direction is this reaction going to go then? Is it going to go to the right or to the left? It's got to go to the right. There's no way for it to go to the left because I can't use any of these to make more A and B because there are none. So we are going to, some A is going to go away, right? X. For every A that's consumed, how many B's are consumed? Based on the equation. 1, right? There's one A and one B, and they come together somehow to make a C, a 2C, and a D. So for every A that's used, a B gets used. Okay? For every A that gets used, how many C do I get? 2. So I've got plus 2X on this side. And for every A that gets used, how many D do I get? 1. See that? All right, that's how we fill this thing out. And then the final concentrations are going to be, I started with 0.50 molar A, and X of it went away, so minus X. I started with 0.20 molar B, and X went away. Okay? And then over at 2C, I started with 0, and I got 2X, so I'm going to have plus 2X here, and here I've got plus X. Does that make sense? Okay. All right, that's how you do one of these. Let's have you practice one. All right. This reaction here, by the way, I'm going to take 1 second to go on a little bit of a tangent. This reaction is it's from the Born-Haber cycle, or it might be just the Haber cycle. I can't remember. Born-Haber got various things. Is it the Haber-Bosch process? Okay, so Haber was on this one. But what this is this is the reaction that's used to take nitrogen from the atmosphere and make ammonia. And it's super important because you take that nitrogen in the atmosphere, you make it into ammonia. Plants can't use this, but they can use that, and they need nitrogen. So it's a way to fix nitrogen to make fertilizers, and that's why we can have, 8 billion people, 9 billion people on the planet right now? Because we're making fertilizer. Otherwise, we couldn't grow enough food for everybody. Anyway, go ahead and fill out the odds table. Yeah, and you're always welcome when we're working problems in class to talk to each other, try and work together to do it if you want to ask people questions. You're also welcome to call me over. Yes?
So I take it that on the exam we cannot use the graphing calculator.
You are not going to be able to use a graphing calculator to do this on the exam. You're going to have to solve. We'll get to the quadratic formula in a minute. So.
Because I feel like you never have to use it.
I hate it too. Okay. There's lots of things we do that are about reasoning in the class that actually the computer can solve, right? As we go, especially with AI, there's lots of things we do now that you'd never have to do your own stoichiometry. I don't do that in lab. But probably AI can just do all your stoichiometry for you, right? I've never tested it. I would hate to get something wrong in lab, get a wrong answer in lab and waste 3 weeks of work. All right, let's go ahead and look at this. So what we've got is we've got our nitrogen. We've got 1 nitrogen's going away, right? An X of nitrogen. If X nitrogens go away, how many hydrogens go away? Hydrogen, when I say nitrogen, I mean N2 and H2. 3. So it's going to be minus 3X, right? Okay. And then how many ammonias am I going to get for every nitrogen gas that goes away? 2. So plus 2X. I'm going to put the plus in to be really explicit about that. All right. And then how about I start with 5 molar H2. How much H2 do I have at equilibrium? 5 molar minus 3X, right? And how much ammonia do I have at equilibrium? Plus 2X. All right. So if you're doing these problems on the test, right? Let's say you're preparing for the test, and what we do later, you have a lot of problems that you're confused with. Remember, show as much as you can, right? We got 3 things here. This is one of the skills. That partial credit for just being able to set that up. Questions? All right. Let's go ahead and we're going to do the next one. This one we're going to have to use a quadratic formula for. Or we're going to solve it, so we're going to have to do that. So what we're going to do is set this one up, and then we're going to solve. All right, this is a problem here. This one's actually done in pressures. And they give us a Kp, right? And then they give us pressures. Great, so I don't have to do any conversions for Kc, Kp, or anything like that. Go ahead and set up the ice table on your own. go up and set it up, and then, well, try to start solving it. I need to step out for a minute because I didn't get to use the. I think I'll be right back.
I can write the solve for it. Negative b plus of b squared minus 4ac. It's like a song for it.
There was a song. Yeah.
I didn't know that for calculus.
That makes sense. So like, I don't know which one.
Yeah. I don't know if we're
This is actually 50 just maples and
I wanted to get
why?
Are you gonna take a math class?
Makes me still mad.
Oh really? What's your math? It's not
You know
like
how
a
easy it is?
prerequisite.
Fix it. Can I fix that?
Oh, okay.
What is it? It's negative b plus or minus plus or minus the square root of b squared minus 4ac. I had to, we had a little song that my teacher said.
Plus
or minus b squared minus 4ac.
I forget the song ever. Our teacher made us do like dances for all the different songs too.
More of a rhythm.
I don't know what the dances were. Do you know what like is?
All right, I'm sorry about that.
Oh, yeah.
Like that type of stuff.
All right, let's go ahead and look at this. So we're going to do an ice table for it. So what I like to do is write this up above. This is, well, it's chloroethane. All right, and it's going to go to make ethene plus hydrochloric acid. And so for your ice table, we've got initial, we've got our change, we got equilibrium, and it tells us what? It's 2.5 ATM, right? So I'm going to put 2.50 ATM here, and I don't have anything else at the start of the reaction because it's not mentioning anything, right? It didn't explicitly tell us there was 0. And then my change, I'm going to have one of these go away, right? And for every one of these that goes away, one of these appears and one of these appears. Anybody confused on how I'm coming up with how many? I'm using the coefficients from the reaction. All right, and then what I'm going to do is I'm going to subtract. So I've got 2.50 ATM minus X, and I'm going to get plus X and plus X. Good with that? All right, so now here, this is where we're going to solve. We now need to solve for X, right? We haven't done that yet. I've got an equilibrium constant, which was equal to, what was it? 0.0996 or 97, 0.097. All right, and that's equal to products over reactants. So C2H4, that's ethene, hydrochloric acid, and we had this chloroethane. All right, sorry about the messy writing. All right, and I can scoot down here. I can still see what my equilibrium concentrations are, and now I need to put them in. So this goes here, that goes there, that goes there. And so 0.097 is equal to X is my concentration on top times X, and down here I'm going to have 2.50 ATM minus X. All right. So now we need to solve this. And this is where it gets a little bit ugly. I'm going to need to multiply this times, it's not ugly yet, but it's going to get ugly. That times both sides. All right. And that if I solve for that, now I'm going to have x squared over here is equal to, if I take 0.097 times 2.5, I need to get rid of this, I need to distribute, so I need to multiply that times that and that times that. So 2.50 times 0.097, and I get, this was giving me conniptions earlier, 0.2425. Kept mistyping into my calculator. And that's positive, and then I'm going to end up with negative 0.097x. Okay, you guys with me? And now I need to get it all on one side. All right, doesn't matter which side. I'm going to move it all, I'm going to make as many things positive as possible. So I'm going to go ahead and subtract 0.2425 from this side. I'm going to add 0.097x. So these go away. Those are going to become 0. And then on the other side, I'm going to subtract. I got to do the same thing to the other side. 2425 and plus 0. 0.097x is equal, oops, no, I'm just add do that. Let's not equal. All right, and then I'm going to rewrite it, and I end up with x squared is equal to, or x squared plus, I'm going to move this over so it's the x's are in order, 0.097x minus 0.2425 is equal to 0. And now we're ready for our quadratic formula. And so our quadratic formula goes as such. I'm going to go, quadratic formula says that x is going to be equal to b plus or minus the square root of b squared minus 4ac over 2a. Okay? How many people have never seen this before? Okay. All right. So if you haven't seen it before, you're going to need to practice it some more. We're going to work our way through it once. But this a is the exponent, or what's in front of this, the x squared. B is what's in front of the x. And c is that final number. And then the other thing I want to point out here is notice that the equation has a plus minus. What that means is we have to try this negative b plus that term, and we have to try this b minus that. And we're going to get two answers. There are going to be two solutions here. All right? And one of them is going to be unreasonable from the perspective of chemistry. In other words, one of them is going to be negative. Can you have a negative concentration? No, it's not possible. So we get to throw that one out and accept the one that's positive. So let's go ahead and do this. What we've got is I'm going to go ahead and, so for the first working, I've got negative, b is this 0.097, so 0.097 plus, I'm going to do the plus version first, the square root of 0.097 squared minus 4 times a is 1, right? There's a 1 in front of the x squared, 1, times c is this number at the end, negative 0.2425, okay? And that's all over 2a, 2 times 1, because 1 is a. Questions? All right. Pay attention if you haven't seen this before. So I've got minus something that after I multiply by this minus, it's going to be minus minus, right? Minus minus is a plus. Minus times minus is a plus. So I can just do that and get rid of it. And now, last hour, I actually got a slightly different answer than everybody else. I must have keyed in something differently. I'm going to see if I do better this hour. Oh, there, I got the answer they got last hour. So that's satisfying. All right, so I'm going to go there. There's my answer right there. That's what x is equal to. Okay. And our units above for x were what? Was this a pressure problem? This is a molar problem, right? No, it's atmospheres. Okay. So that's atmospheres. Okay. Let's do it the other way. Yes.
What happens to this? Well, I guess maybe it goes away when you do like, but what happens to the negative in front of the first A?
So what happens to this negative right here? So what happened there was this was much bigger than this. Okay. And so I subtracted, it was still positive. But what that tells you is you can look at it right now, okay? And you can look at it and see that, all right, if I just did it, this thing, when I did the plus, right, because it's plus minus, if this thing wiped out the negative there, well, the next time it's going to be this minus this. And so this is going to be the negative. But I'd accept that sort of reasoning if you wrote real quick. I'm not, the other one's going to be negative. Does that make sense?
Yeah.
So what I'm going to do here, though, is I'm going to demonstrate the height of laziness, and I'm going to copy this down again. Maybe not. There we go, I am. And then we're going to solve it again. I'm just going to change the sign, right? So do you see, if you haven't seen this before, where's our first quadratic formula? Where do we put there? Right here. Okay, so we're right here. We just did the plus form. Now we need to do the minus form. All the numbers are the same. That just becomes a minus. So rather than rewrite all those numbers, I'm going to save some time in lecture and just make that negative, right? Now we're doing the minus form. Go ahead and we'll put that through our calculators. And you can't use a graphing calculator to solve it. I think you guys already asked that. Certainly the other class asked it. Well, there's my square root key. All right, and so I've got negative 0.43 ATM. And so just like you can't have a negative concentration, there's no such thing as negative pressure. All right? At least if you're thinking about inside a vessel, there's no such thing as negative pressure. Does that make sense? Okay. You could have a difference in pressure between two things, but. And so this one goes away because the negative number is nonsensical from the perspective of chemistry, from the real world. Questions on what I just did there? Yes?
So we always want to work out those, correct?
You always want to work out both, but I would say, you're on a test. I would accept you're on a test, you're doing it, the first one ends up being positive, and you go, well, the other one's going to be negative.
Okay.
One will always be nonsensical.
Okay.
Okay. So I would accept that. However, if you made a mistake and you got the negative one and made it positive somehow, that's not going to save you.
Yeah.
I would encourage you, if you get this on a test, okay, write all that out. so I can see what you put in, because if you make some sort of calculator mistake, then I can give you most of the credit for it. Does that make sense? Right? I don't take off much in terms of calculator mistakes if I recognize them as such, but I need work to see that. Okay. All right, so that's how we solve that one. So but let's go back to this real quick. So 0.446 atmospheres. Let's go back to our original problem, way up here where we have the ice table. So what that means is X is 0.446 atmospheres, right? So what's the concentration of this at the end? Or the pressure? It's X, right? From down in our ice table, which was 0.44 atmospheres, right? 0.45, I guess, if I'm rounding like that, because it was 0.446. How about this one? 0.44445 atmospheres. Okay? And what about this one? It's 2.5 minus 0.44 or 4.45 atmospheres. So 2.50 minus 0.45 equals 205 is what I've got. So 2.05 atmospheres. Does everybody understand what I just did there? Okay? That's solving the final concentrations, which is what we're after. Questions? Okay, so we all hate the quadratic formula, right? So let's talk about how we can avoid using it sometimes. Yes. So what we're going to do is we're talk about the approximation that lets us avoid using the quadratic formula. Okay. All right. So we can avoid the quadratic formula when our equilibrium constants are really big or really small. I'm going to say really, really big. All right, let's stop there. Really, really big. I'll fix equilibrium in a second. Let's say I've got an equation. A plus B goes to C plus D. And so my equilibrium constant is going to be equal to, it's a big K, it's going to be concentrations of products over concentrations of reactants. All right. And so if K is really, really big, am I product favored or reactant favored? Product favored. It means this is really big compared to this, right? Does that make sense? If this is really big. So what we're going to say is when the rate constants are really, really big, almost all products. Okay? Or when the rate constants are really, really small. Not rate, equilibrium constants. And when they're really, really small, that means this is really large compared to that. And so I have lots of reactants, almost all reactants. Okay. In these cases, the changes in the almost all thing can be neglected. Okay, and we'll talk a little bit more about it in a second. The almost all thing are, I'm going to say can be neglected. Well, let's not say the changes. We can neglect things. right? It's not the changes, because if I started out with some products, right, and had a really big equilibrium constant, the change is going to be big to these. But essentially, you're going to say, okay, what are the concentrations of these? It becomes all this. And you're not going to worry about the X. You're not going to worry about some small amount that isn't there. You're just going to assume it all went. And then you're going to calculate the tiny bit that's left over, if that makes sense. That's not going to be our example. Our example is something that's really small down here, okay? And let me give you a guideline for that. Really, really big is this, and I don't want to do my exponents. Really, really big, really, really small is, so really, really big is greater than, and really, really small is less than, and then let's just say big is going to be 10 to the third, and small is going to be 10 to the minus third, okay? So we'll just use those as guidelines. All right, so we're going to skip this problem. I just made it nice and big. We are going to skip it. This is because it doesn't have an equilibrium constant, right? We look at our equilibrium constant, what is that? 2.9 is neither really big or really small. Just 1 second. All right, so here's the problem we're going to do. We're going to look at a question.
I'm so sorry, could you just scroll back up for like 2 seconds?
Yeah.
I'm so sorry. Okay, got it.
Everybody got that? 10 to the minus 3 is big or bigger. 10 to the minus 3 or smaller is really small. Okay. So looking at this problem, this one we can do the approximation with, so we're going to use that one for practice. All right, we only have so much time left, so we're going to have time to do one of these. We're going to do Le Chatelier's principle, which is super cool, and then that's going to be the end of the material for the test, and probably the out of time point for the lecture as well. So we've got this acetic acid equilibrium on the top here, and what the question is asking us for is you start out with 1 molar of whichever acid you're looking at here, and what's our final concentrations going to be? Okay, we start out with that, we let it come to equilibrium, what's up? And so we have this one, I guess the other one, oh no, it's -1, so that's not going to be good. So here, what I'm going to do is let's go ahead and set up our ice table. Right? We've got that is going to be in equilibrium with H plus, and that. This is acetate. This is vinegar. So when you think about the acid and vinegar, acetic acid is the acid and vinegar. All the different tastes of vinegar that you may have experienced in your life, they're all just like trace quantities that give flavor. So we're going to do our ice table. So initial change. Our initial concentration is 1 molar. Was it 2 significant figures? Our initial and we start with no products, right? Yes.
What was the K?
The K is 1.8 times 10 to the negative 5th. We'll bring it down. We're doing it as well. So now, what's our change going to be for acetic acid? It's going to 1 goes away, right? X. So we have X go away. If I have X of acetic acid go away, how much H plus do I make? Plus X. And how much acetate ion do I make? Plus X. All right. And then when I'm done, I'm going to have 1.0 molar minus X, right? And then I'm going to have plus X and plus X. Get ready to cross something out. All right. Right now we're set up to do the quadratic equation. But this is super small. So it favors what? Reactants or products? Reactants. What it means is barely any of this is going to dissociate to make these 2 ions. And so this number is going to be really small compared to this. And so it's essentially going to be 1 molar when you're done. Okay, it'll be tiny, tiny difference that when we do our sig figs is just going to go away. And so this goes away. And so now when we set this up, we had, was our equilibrium constant was it 1.8 times 10 to the negative fifth? Yeah? Okay, and that's equal to products over reactants. So our products are H plus ion and acetate ion. And our reactants are acetic acid. Right? And so now I want to put these things in. I'm going to go ahead and put 1 molar there, and I'm going to put the X here and the X here. So let's go ahead and rewrite it. We've got 1.8 times 10 to the negative fifth is equal to X times X squared, over 1.0 molar. Right? And now we will not have a quadratic equation because we're going to end up with X squared. We just need to get that over there, and then we can just take the square root. Okay, much easier. And so let me rewrite that. I'm going to actually multiply both sides by 1.0 molar to make these go away. 1.0 molar. Okay. And if I rewrite this and I multiply those x's together, I end up 1.8 times 10 to the negative fifth is equal to X squared. And so I can take the square root of 1.5 times 10 to the negative 8. Negative fifth, sorry. I'm going to take the square root of that, and I am going to get 0.0042 molar is equal to X. Okay, do you agree with me that 1 molar, that if I've got two significant figures on my 1 molar, right, and I subtract 0.0042, then I'm going to lose that in my significant figures, so I don't need to worry about that. And so when we think about, let's remember 0.042, so when I think about what are my final concentrations here, what's the, if we look at our ICE table, this was, just up a little more, there we go. This was X, this was X, and this just doesn't change when we think about our significant figures. So our final concentrations would be 0.0042 molar, which is what we solved for there, right? This is also the same based on, because that was also X, and then this just ended up being 1 molar to two significant figures. Questions on the approximation, how we did that? When you can do that? Yeah. I'll scoot down. I will post these notes, and thankfully my computer is still tracking. All right, we're going to have about 5 minutes left for the Le Chatelier's principle, which is great. Okay. Yeah. See how much time we have? We have tons of time. We don't leave until that gets up to, well, before, right? Okay. Questions before I go on? I'm good. Yes.
What would you say for the concentration of like H, like sig figs was?
So we're talking about H plus?
Yeah.
That's this. So remember our equation was this. So it was HC2H5O2, that's acetic acid. Okay, and that's in equilibrium with this dissociating to make H plus. I'm going to leave my states out, but maybe I'll put them in because I'm a stickler of that sometimes on quizzes. So this is aqueous, this is aqueous, this is also aqueous. Okay, and so our concentrations, this was that and that. Does that answer the question?
Yeah, I think I just saw the sig figs wrong, but it makes sense now.
I'm just taking two
Why
sig
does it
figs
work?
because I have two sig figs up above. Yeah, Elise.
When you write out the equation and everything,
Uh-huh.
you just put like without the phase changes, like the aqueous.
Yeah.
On the test, like, do you care if it's in there?
I care if I say complete the reaction.
Okay.
So I think on one of our quizzes I said, hey, what happens here? What's the reaction? And I care, complete the reaction, you need to show me what the phases are, because I'm asking about that.
Okay, so just.
For this, I'm not really gonna care, right? And you're probably not gonna be complete in the reaction, because it'll probably be given to you like up here, where they give them to you. Right. Okay. All right, we've got 4 minutes. So let's talk about Le Chatelier's principle. I was going to look up, I just was too busy. This is French. I always never know how to spell this. Le Chatelier's. Is that it? Who's got French? All right, well, that's not right. It's going to be the other way. And then I'm going to move on. L-I-E-R, I think so too. I can never spell this, but it's Le Chatelier's principle. And this is really, it's really cool. And it's also really important or really useful. Okay, it's not just a fun thing that I like to talk about. So when I talk to my biochemistry class, I start off and I say, we've got 3 rules we're going to apply this semester. The first one is that you can explain most of chemistry using charges, right? You've heard that from me before. Okay. The second one is you can use Le Chatelier's principle to apply to everything. Okay, and I've applied, when I was a student, I applied this to everything. It's really useful. And what it says is that a system at equilibrium when perturbed will adjust to come back to equilibrium. Okay. All right. And so what that means is if I've got something at equilibrium and I add products, it's going to shift towards reactants. So example, if I add reactants, well, products, right? I said products. Add products to a system at equilibrium, it will shift towards reactants. All right, and we're running out of time, so I'm not going to actually write much more there. I'm going to give you an example. So in your body, you have what's called the bicarbonate buffer system. All right, and what this does is this system is going to buffer how much acid is in your blood. We haven't talked about acids yet. I'm looking forward to doing it after we get back. Essentially, this is going to make it so your blood doesn't get too acidic or too basic. All right. H+, you can think about it, H+ as acid for now. We haven't talked about pH yet, so I can't use pH. But, so I've got this going on in my body. This system is going to shift back and forth to regulate how much acid I have. So right now, I'm talking to you, and I'm actually breathing out while I talk to you, right? And as I breathe out, I'm breathing out 4% carbon dioxide. And I'm breathing in something like 0.04% carbon dioxide, okay? So when I breathe out in my lungs, I'm getting rid of carbon dioxide. I have this equilibrium in my body, but when my blood gets to my lungs, carbon dioxide is leaving. If carbon dioxide leaves, this is what's going on in my lungs, this reaction will shift over to that way, okay? So it shifts left. That makes sense? I breathe out. So it's something, if you do the math, it works out this way, but it shifts left. Okay, I'm going to do 2 more of these. Make sure this will be on the test as well because it's so useful. In my kidneys. All right, if I don't have enough, so when this shifts left, I have less H+. My lungs and your lungs are less acidic than the rest of your body. Okay, if I have not enough acid in my body, alkalosis you may have heard of, then my kidneys are going to get rid of bicarbonate, and this reaction is going to shift right. Okay? And when it shifts right, it's going to make more acid. Does that make sense? One more. Okay, let's add something. Let's do something unnatural or bad for me. I'm going to go ahead and I'm going to drink vinegar. Sounds fun, right? All right, that's going to add acid to my body. And what's going to happen is I drink vinegar, I'm going to shift that way. I'm actually going to make more carbon dioxide. Shifts left. Does that make sense? So if I drink vinegar, it'll shift this way, and I'll actually make more carbon dioxide. Questions on that? Come up and ask questions afterwards. Thanks for staying an extra couple minutes at your point. See you guys in a couple days. Have a good couple days. If you need help, please come get it. Yes.